Okay, welcome to the NUPOC video study guide number 68. We're going to continue with some physics problems here, and we're going to look at a dynamics problem where we have this this cart that starts at the top of some hill that has height h, and we release it and it accelerates down the hill due to the force of gravity, and it eventually hits this plateau, where it starts running across like this, and then it hits this loop of radius r, continues through the loop, and strikes this spring at the end. And we're interested in what minimum h, what minimum height is necessary such that this cart has enough velocity, right, when it enters this loop, that it makes it through the loop without gravity causing it to come crashing down at the peak of the loop. And we're also interested in what the displacement of this spring is once the cart makes it through the loop and then strikes the spring. So we want to start by taking a look at this this loop. And so I've drawn it a little bit expanded here, and so we have this loop of radius r here, and we have this cart, and the cart has mass m, right? And it travels through the loop in this direction. So it comes in here, goes through the loop, and then exits this way. So we want to make sure, right, that when the cart reaches the top of the loop here, right, like this, that gravity doesn't cause the cart to come crashing down. And so no matter where the cart is in the loop, we can say that gravity, the force of gravity, right, is always trying to pull it down, okay? But of course, at this point on the track here, we have the normal force of the track pushing back on the cart, right, so that it doesn't accelerate down through the track. Okay, it supports it. The track supports the cart. Now here you can see that the original velocity vector of the cart when it came into the loop was in this direction, in the direction of my pen. But as it starts to go around the loop, the velocity vector starts to change, right? After it's gone a little bit into the loop, the velocity vector is like this. And so if the velocity has changed, even if the magnitude doesn't change, of course it does change in this case due to kinetic energy being given up to potential energy, but even if just the vector direction changes, right, there must have been some kind of acceleration. And that acceleration is caused by a force, and in fact it's caused by the normal force of the track. So the track starts pushing on the cart, right, as it goes through this loop, and causes it to accelerate and change its velocity vector as it goes through the loop. Now from the cart's perspective, or if you were in a seat in the cart, you would in fact feel the normal force, right, pushing back on the track. So the cart, in fact, because we know that the velocity vector is just changing, right, this cart, even though we have this normal force pushing this way, the cart isn't flying off in this direction, right? It's just changing the magnitude of the vector. So in fact, the normal force, right, the cart also pushes back on the track with the same normal force. So that's what we're going to call the normal force in this problem, right? Is the force of the cart pushing back on the track. So if we come all the way to the top of the track here, we can see that in this case, right, we have the force of gravity, right, pulling us down, and the cart also experiences a force, right? The cart experiences a force, a normal force, right, which has a vector, so it's a little bit crowded right there, all right, pushing back on the track, okay? And this is only the force that the cart experiences, right? Because the track also has a normal force pushing back on the cart, and then it translates that force to, you know, maybe pushing down on the ground or something like that. So these are the forces that are just seen by the cart, from the cart's perspective, not the track, right? And so at the very top of this loop, we want, if we drew the cart out upside down at the top of that loop, right, we have the force of gravity, mg, and we have the normal force, which, by the way, is mv squared over r, the radius of the loop. And I'm going to call this vt squared for the top of the loop, right? And so at the very top of the loop, we want these two forces to be equal and opposite. So we want these two numbers, these are the magnitudes of the force, right, to be equal. So we can say that mvt squared over r equals mg, and of course we can cancel the m's, and we can see that we want vt to be equal to root rg. And that's a minimum. That's a minimum vt that will get this cart through the loop. So right at the very top of the loop, the magnitude of the normal force and the force of gravity will be equal, their directions will be opposite, and there will be a moment of more or less weightlessness for the cart. There'll be no net force acting on it. So if you were riding in this cart, you would feel a brief instant of weightlessness right there. Right? So now how can we use this to find what the minimum height for the hill should be? Well, now that we know the minimum velocity of the cart at the top of the loop, right, we can find what the velocity is when it entered the loop, because we can take this potential energy that it gains from coming from the top of the loop back to the bottom and find out what the initial velocity is. And we're going to call that VB for V bottom. So we can say that the kinetic energy at the bottom, right, which is 1/2 m VB squared, is equal to the kinetic energy at the top, or 1/2 m VT squared, plus mgh, but h here is of course 2r, right? So m2 mgr. And we can multiply everything by 2 to get rid of the 1/2 and turn this into a 4, right? And we can cancel out all of our m's. And if we go ahead, we're interested in what the velocity at the bottom is, VB, so let's just go ahead and take the square root of both sides. And what we'll end up with is VB equals root VT squared, but we know the VT minimum is root RG, so it's root RG squared, which is just RG, right, plus 4GR, or just 4RG, which is root 5RG. And of course it's, plus minus root 5RG, but we know that, the velocity vector, we're going to say it has a positive value going in this direction, and we're going to choose the positive root. Okay. So now that we have the velocity at the bottom, right, the velocity of the cart here, this is VB, right, and this is VT, right, we can figure out what the initial height must have been by converting the kinetic energy due to VB entirely into the potential energy at height h. So we can say that the kinetic energy at the bottom, or 1/2 mVB squared, or 5RG squared, right, which is just 5RG, equals mgh, right, mgh. Our m's cancel, our g's cancel. We can bring this 5 and just put it on top of the 2 there. So what we have is h equals 5/2 r, right? Or 2.5 times r. And of course it passes a sanity check, because h must be greater than 2r, because we must start at least somewhat higher than the loop in order to have at least some kinetic energy when we hit the top of the loop. But this is the minimum h, right, where if we release the cart, it would go down and gain some speed, it would accelerate and gain speed to this plateau, barely make it through the loop with a moment of, an instant of weightlessness at the top, and then come back out of the loop with velocity VB again. Now, how do we look at the displacement of the spring here? Well, we can say now this kinetic energy due to VB, which is again 1/2 mVB squared, or 5RG, right, is now going to be equal to all the potential energy, right, that goes into the spring, or 1/2 K, right, the spring constant is K, x squared. And of course we're interested in x, so we can cancel out these 1/2. We can bring the k to the other side of the equation here and take the square root, and again we'll take the positive root, and we'll say that the displacement x, starting from this point here and positive in this direction, right, is root 5 mRg over k. So there we go. We have some hill with a minimum height of 5/2 r, where r is the radius of this loop. And when the car goes through the loop, it ends up hitting the spring and displacing it by root 5 mRg over k.